Good morning, boys and girls. Welcome back. Today we are talking about optimization and doing some optimization problems. These are really some of my favorite problems to do. I think they're kind of fun. And these are problems where you're trying to minimize or maximize something. You've really kind of done these a little bit before in trig pre-calc I guess just in trig pre-calc. Where, I don't know if you remember these problems, but you've got something like the farmer who's trying to do a pen along a river, and he wants to maximize the area, or he wants to minimize the amount of fence used, or, and we have some rules that we got to kind of go by. Only now we're going to, instead of solving these things with polynomial functions, well, we're still going to use the polynomial function, but we're going to use our calculus to be able to solve it a little bit easier and not have to rely upon the graph. All right. So the trick to these problems, is there's two parts generally when you read the problem. There's an objective function, and that is the thing you're trying to minimize or maximize, and there's a constraint, and that's the restriction on the scenario. Okay? I think oftentimes people that have a hard time with this get caught up in the constraint of the situation, and they forget about the objective function. All right? So whenever you tackle these, try to write your objective function first. All right? Okay, so here comes our first problem we'll talk about with the objective function and the constraint r. Okay, so here is our first problem. Find two positive numbers that have a sum of 20 and whose product is a maximum. Again, we said we have a constraint and we have an objective function. And again, you want to start with the objective function, the thing that we're trying to minimize or maximize. So in this case, hey, we want to find whose product is a maximum. So we're trying to maximize the product. All right, so this is my objective function. The product equals two numbers that multiply each other, right? Two positive numbers, x, y. So there is our objective function. That's what we want to do. Okay. Now, after you write the objective function so you realize what you're going to try to minimize or maximize, now you want to deal with the constraint. The constraint on this situation is that we have two positive numbers that have a sum of 20. Because a constraint is often easier to write than the objective function, I think that's why we start there sometimes. But try to zero in on what you're going to try to minimize or maximize first, and then come to this constraint. Okay? Two positive numbers that have a sum of 20. So x plus y equals 20. And again, in this case, I used x plus y. You could use a and b. It doesn't matter the variables you are using. Once you have your objective function, your constraint written down, what you need to do is try to write your objective function in terms of one variable. All right? So in this case, I'm going to solve for y. So y equals 20 minus x. You get to solve for x too. It doesn't matter. Now I'm going to come over here and I'm going to plug in to my objective function. Instead of y, I'm going to put 20 minus x. And now I've got the product is 20x minus x squared. So that's our goal. Write your objective function, write your constraint, write your objective function using the constraint in terms of one variable, and now you just need to find the minimum or maximum of this function. Right? So to find the min or max, we take the derivative. Right? So p prime equals 20 minus 2x. We're going to set that equal to 0 to find our critical values. And I get 2x equals 20 or x equals 10. Now, I guess we should double check to make sure that this is going to be a maximum value. So if I do my line test and put 10 in the middle, anything smaller than 10 when I plug it into the derivative here, like if I plug in 0, I get a positive number. And anything bigger than 10, of like 100 I plug into here, I would get 20 minus 200, and that would be negative. When you do this, notice this says I'm changing from increasing to decreasing on the derivative, from positive to negative, so that is a max value. Here's what we're going to say when you're doing this. If you only get one value, though, and they ask you to find a maximum, that's going to be the maximum. You don't have to test this every time. Or if they say find the min and there's only one critical value, you're going to be able to assume that that is a min value. Now, if you get multiple critical values, you better start testing to see which is the max and which is the min. But generally speaking, we're going to get just one critical value, and that's going to be the one that we can use. All right? Now that we know that x is 10, now I can go back here and find the y. 10 plus y equals 20. And now I know that if I subtract 10 from both sides, y has to be 20. So the two positive numbers that have a sum of 20 and whose product is a maximum is, make sure you answer the question, 10 and 10. All right? But see, optimization isn't that bad, and that was kind of fun. Here we go, on to our next one. Okay, here we go, number 2. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Now, if this were me, first thing I'm going to do is I'm going to draw a picture. You know I'm a sucker for a good picture. I mean, look at this, especially when you get to use colors. Oh, man, it doesn't get better than that. All right, once you have a picture kind of drawn that you kind of work from, I think the next thing we want to do again is try to figure out what our objective function is. Figure out what are you trying to minimize or maximize. All right, so in this case, we are trying to find the what dimensions, again, this normally comes at the end of the problem, what dimensions require the least amount of fencing if no fencing is needed along the river. All right, so we're trying to minimize the fencing. We want the least amount of fencing, so minimize our fencing. So let's put some variables on our picture and see if we can come up with an objective function. All right, so I called this side here x and this side here y. And what we're really trying to, to minimize, if it's the fencing, then is the perimeter. So I called it p. And again, it doesn't matter the variables you use, but these are the ones I'm most comfortable with, so that's what I'm using. And I know in a rectangle, the opposite sides are the same, so this is also x. So p, the perimeter, is 2x plus y. There's my objective function. That's what I want to minimize. Now I have a constraint on the situation. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. All right. So if the pasture must contain 180,000 square meters, that would be the area, right? So 180,000 equals, running out of room. X times y would be my constraint. Okay. 180,000 equals x times y. All right. Now I want to use this to write my perimeter, my objective function, in terms of one variable. Okay, so I took my constraint here. My work's a little bit crazy. And I divided both sides by x to get y by itself. So I got 180,000 over x. And then I took and I plugged that in for y in my constraint. So p equals 2x plus, instead of y, 180,000. And I wrote it as x to the negative first, since I'm going to have to take the derivative. That will make my derivative a little bit nicer. Now that I've got my constraint, or my objective function, written in terms of one variable, now I'm going to go ahead and take the derivative to find the min or max. All right, and there's our derivative. Again, very important when we're doing this that we notate properly. Okay, please let people know you are taking the derivative. Please let people know what your objective and constraints are. You know, make sure you're labeling things appropriately. Now that I've found my derivative, I'm going to set this equal to 0. And I'm going to go ahead and solve for x. So 2 equals 180,000 over x squared. If I add that term to both sides and rewrite it. Or if I multiply it by 2x squared equals 180,000. Or divide everything by 2 and I get x squared equals 90,000. If I square root both sides, we get x equals 300. And now again, if I plug that back into my constraint, I'm going to get y equals 600. Now, again, because I only had one value here, well, I guess I got plus or minus. I should have got plus or minus 300, right? But the fence can't be negative 300 long, so I got rid of that one. So I really only have one critical value that works. And so I knew that that was going to be the one that minimized this. And so I know that these are my correct dimensions. 300 meters by 600 meters. And again, make sure you don't just, your answer is not x equals 300, y equals 600. That tells me nothing. Answer the question. The dimensions of the fence would be 300 meters by 600 meters. Answer the question just like that. All right, moving on. Next one. Okay, here we go. Number 3. We're going to determine the dimensions of a rectangular solid with square base of maximum volume if its surface area is 150 square inches. All right, so square base, so that is x, and then that means the length is y. We're trying to maximize the volume. That's our objective function. So to write the volume of this would be area of the base times the height. And then our constraint on this is the surface area. The surface area would be 2 times the areas of the bases, right, for the top and bottom. Be careful on this. Make sure you're reading closely sometimes. You're like these problems, we're usually talking about boxes. And sometimes it's an open top box, and so you would not include one of those bases. But in this case, it's just a rectangular solid, so we have 2 bases. And then we have 4 sides, right? 4 of these sides here. So 2x squareds, the front and the back, or the top and the bottom, and then 4 of the sides right here. And that is my surface area. And now, again, that was our constraint. And so instead of writing surface area, I want that to equal 150. And now I'm going to write my objective function in terms of one variable. If you look again here, I chose to solve for the y variable. I think that's going to be the easiest. So I got 150 minus 2x squared over 4x. And then I just simplify, divide the front and the back by 4x. And I've got this expression for y right here. And so now I want to go and plug that back into our objective function so that I can take the derivative. Okay, plug in for the y here. And I distribute my x squared. I get 75 over 2x minus 1/2 x cubed. Now I'm going to take the derivative. And we get 75 over 2 minus 3/2 x squared. Now we need to take this and set it equal to 0 and solve for x. All right, solving for x, I put the x squared on the other side, multiplied both sides by 2, divided by 3, took the square root of both sides, and I should have a plus or minus. However, again, the cube cannot have a negative length, so I discarded the negative answer for the positive, and since I have just one, I know I'm okay. Now, I want to take this, I'm going to plug it back in to find my y value. And I plugged in up here to this equation right here for it. And again, I get 5. So, now I need to answer my question. What are the dimensions of a rectangular solid that has the maximum area in this surface area? And that is a cube, it looks like, when it's 5 by 5 by 5. Okay, would be the dimensions of this rectangular solid. I can't remember if there were units. Were there units? Square inches. So I probably should have inches on all these things. Don't forget your units, especially if it asks you to write your units down. Okay, one last one. A rectangle is bounded by the x-axis and the semicircle y equals 25 minus x squared. Square root of that. What length and width should the rectangle have so the area is a maximum? All right, step 1. Draw a picture. Through the problem and through the equation given, you should know that, again, the top part is a semicircle with a radius of 5, right? And on the inside, we're inscribing a rectangle, kind of like that. I can say that the base of this half of the rectangle is my x-coordinate, or x, and then the height of the rectangle is y. Okay, now what we're doing is we're trying to maximize the area. Area is a maximum. And because this is symmetric, if I maximize the area in this half of a rectangle, then I'm really going to maximize the area in the whole thing. So I wrote my objective function as a equals xy, just to keep things a little more straightforward. The constraint in this situation becomes the equation of the circle itself, or the semicircle itself. So here is our objective function written in terms of one variable. Now I just need to take the derivative. In order to do this, we need to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. Don't forget chain rule when you do this. I'm going to tidy that old answer up a little bit and just make things a little nice, combine my like term stuff. And then again, like normal, I'm going to, before I set this equal to 0, I'm going to GCF it so that I'm going to be able to solve. When you GCF, again, you're always going to pull out the lowest exponent. So I pulled out a 25 minus x squared to the negative 1/2. Inside of those, a 25 minus x squared. That went to the first. Minus x squared. Or 25 minus x squared to the negative 1/2 times 25 minus 2x squared. Now I now need to set that equal to 0. Okay, when I set this first piece equal to 0 over here and I solve this, this is technically where the derivative is undefined since that's a negative exponent and it's going to be on the bottom. But those are still critical values. But I get plus or minus 5 and those are the endpoints. And if x is plus or minus 5, then it's going to have no area because there's nowhere for the rectangle to go up. So I can get rid of these and these are not possible solutions. So the ones I'm really looking at are plus or minus 25 over the square root of 25 over 2. Okay, when I set this piece equal to 0. However, again, x cannot be a negative amount, so we're just going to say x is the square root of 25 over 2. Now, going back to the original up here, x was just half of this. So I can't forget, I want the whole dimensions of the rectangle, so I need to multiply this whole thing by 2. And so I get the base of the rectangle should be 2 times the square root of 25 over 2. And when I take my x value and plug it back into our constraint, the y equals square root of 25 minus x squared, I get that y is the square root of 25 over 2. And so my dimensions are right there. There is our answer. Good job, boys and girls.